Hi, everyone. Last time we talked about using sample statistics as point estimates for population parameters. We used the sample mean, x bar, as the best point estimate for the population mean, mu. We used the sample standard deviation, s, as a good point estimate for the population standard deviation, sigma. And we used the sample variance, s squared, as the best point estimate for the population variance, sigma squared. Now we're going to use p hat, a sample proportion or probability, to estimate p, a population proportion or probability. All right. So this is now the fourth column in our table. We're going to let p denote a population proportion, although it could also represent a probability, such as the success probability p from a binomial NP distribution. So this is the part of the class that's of interest to politicians and also to gamblers. Politicians will look at things in terms of population proportions, proportions of voters that support the candidate or politician, and gamblers will look at probabilities that they want to estimate. Now, before, I would give you a binomial NP distribution, and you would calculate probabilities or manipulate probabilities based on that distribution, maybe even approximate it with a normal distribution. But now we're going to do the reverse. Given a sample size or number of trials, little n, I'm going to have you perform a random experiment. I could give you a coin, and we're not going to assume it's a fair coin. It might be a magician's coin. And I might say, hey, flip this coin a whole bunch of times, and based on that random experiment, let's estimate the value of p, the probability that the coin comes up heads, let's say. So we're going to reverse the problem. We're going to ask the inference question. Based on sample data, what can we infer about a population parameter, like this probability in a binomial NP distribution? So to reiterate, we can think of p hat as representing a sample proportion to estimate a population proportion or probability. So remember, a success is a property that we are interested in. So for example, a politician would say that a success is a voter who is going to vote for the politician. A gambler might say, hey, I like heads. A success is when this coin comes up heads. So let's look at it from the politician's perspective. Let's say that the politician wants to know the proportion of voters, registered voters, or likely voters maybe, in his or her state, who will vote for that politician. If n is the sample size, like the number of people in a poll, let's say of 800 registered voters in California, and if x is the number of successes in the sample, so the number of people in the poll who support the politician, then the sample proportion of successes is given by p hat. The sample proportion equals x over n, the number of successes divided by the sample size, which makes sense, as we'll see. If you're a gambler, and if we give you a coin, a magician's coin, so we don't know if it's a fair coin or not, and let's say that you like heads. Heads is your favorite side of the coin, and you want to estimate p, the probability that the coin comes up heads. So p is the actual physical probability that the coin comes up heads. Well, you could flip the coin a whole bunch of times and estimate p by using a point estimate, p hat. If n is the number of trials in a binomial experiment, n here would be the number of flips of the coin, and if x is the number of successful trials, the number of times the coin comes up heads in that experiment, then our point estimate for p hat, this p is the success probability per trial in a binomial NP distribution. Our point estimate p hat is given by x over n. Same idea as before. It's the number of successes in our experiment over the number of trials. It's the same basic idea. So this would be the sample proportion of successes among the n trials. In both cases, x over n. P hat is x over n. So let's apply this idea to an example with two parts. Well, really two examples. Let's apply this idea to two examples, both with two parts. All right, so in example 2, after a national presidential election, a random sample of 500 people who voted in the election are interviewed. 300 of the 500 interviewees voted for the Purple Party candidate. And let's assume they're telling the truth. Actually, and we've seen this before, maybe the Purple Party candidate won, and then the interviewees in the poll might be going, I might be in trouble if I say I didn't vote for the winner. But let's set that aside. Let's assume that these interviewees are telling the truth. 300 of the 500 interviewees voted for the Purple Party candidate. Part A, find P hat, the sample proportion of the interviewed voters, the interviewees, who voted for the Purple Party candidate. Part B, what is a point estimate for the actual population proportion of voters in the election who voted for the Purple Party candidate? So maybe this is the result of an exit poll, and maybe we don't actually know what the results will ultimately be for this election. This could be an exit poll. All right, Part A, find P hat, the sample proportion of the interviewed voters who voted for the Purple Party candidate. Well, it's given by x over n. P hat is given by x over n. The number of successes, 300, that's the number of people who said they voted for the Purple Party candidate. Let's assume they did vote for the Purple Party candidate. So from the Purple candidate's perspective, a success is a voter who voted for him or her. We divide that by n, which was the number of interviewees. We're dividing by little n. Okay, big N could be in the millions, but little n is 500. X over n, 300 over 500, or 0.6. That's our value for P hat, the sample proportion of the interviewed voters who voted for the Purple candidate. So basically, in this exit poll, the Purple candidate is getting 60% of the vote in this exit poll, But then, based on that exit poll, what is a point estimate for the population proportion of voters in the election who voted for the Purple candidate? So this is the actual population proportion among the millions of voters who voted in the election. We weren't able to do a sample. We weren't able to do a census, so instead we looked at a sample. All right. What is a point estimate for the population proportion of voters in the election who voted for the Purple Party candidate? Well, it's going to be P hat, the 0.6. If the exit poll said that 60% of the voters voted for the candidate, because 60% of the voters in the exit poll voted for the Purple candidate, then we're going to infer from that. That 60% of the voters who voted in the election voted for the Purple Party candidate. Later on, we'll talk about margin of error and uncertainty and sampling error and all that. But our best point estimate based on the exit poll here is 60% or 0.6. That's our best point estimate for the actual population proportion of voters in the election who voted purple. And in the end, in the election, that's what's going to matter. So, for example, if the purple candidate gets 60% in the exit poll, but only gets 40% of the vote in a two-way race, then the Purple Party candidate isn't going to be so happy with the result of the election. By the way, that probably means your poll was terrible. I mentioned before sampling error and margin of error. We're going to talk about those issues next. And we're also going to talk about confidence intervals and interval estimates. What if you're allowed not just a point estimate for a population parameter, but a whole interval or range of values? That's next time.